Okay, welcome everybody. Thanks for coming here. And this week we're very happy to have Harsha here, who is a professor in Purdue University and also currently IAS fellow. And so you might see him around more often during the lunches. And we're very happy that he's going to talk about his work today, titled Pathwise, Relaxed Optimal Control of Non-Markovian Systems. Please take it away.
Thank you. Thank you, Walt and Nando, for the kind invitation to talk in this seminar series. So this is not exactly complex systems or emergent phenomena, any of that. It's more a tool, I think, that people in this community could use on their own work. And in particular, it's kind of motivated in some sense by relevant estimation, which I think is something that people here care about to an extent. So really a story about trying to develop a framework for reinforcement learning in continuous time, and when you have non-Markovianity in your system. So if you look at standard reinforcement learning algorithms and methods, they are intimately tied to Markovian assumptions, typically developed in discrete time. So we're asking, how can we go beyond this? And what kind of stochastic analytical tools do you need to go beyond this? Okay, so this is joint work with Prakash Chakraborty, who is at Penn State, and Sami Tyndall, my colleague at Purdue. And Prakash was actually our former student. Okay, so here's a very broad outline of the talk. I'm not going to sort of it's going to follow this layout, but there's a lot of stuff within each of these sections, let's say. And this is based on a recent paper that we put up on arXiv. So I'm going to start with some motivation. I just want to convince you that this is an important problem to an extent. And then I'll briefly talk about classical control and its relationship to RL and how it motivates the questions that we're asking. And then get to this pathwise rough control framework that we have and its relation to RL. So really, this is a story about control, not so much reinforcement learning, but towards the end, I'll tie it together to a RL question. Okay, so I thought since I'm here in the Netherlands, I should have at least one figure. There are no figures in this talk, so I have to apologize upfront. So I thought I should have at least one figure, and I really like MC Escher sketches. And so one of the nice things about being here is I finally got to go to the Escher Museum in The Hague. And this is one of my favorite sketches that he did. And so the nice thing about this image is, it has both convex and concave elements to it, right? So if you look at, let's see if I can annotate this. Okay. So if you sort of draw a line through this image, the right hand is sort of looking up, right? And the left-hand side is sort of looking down on the scene, on the street scene, right? Do you see that? So if you look at this, this guy here going up the ladder, right? So he's sort of, climbing up the ladder. And you look at this woman, she's sort of climbing down, this pathway. So depending on what you're looking at, you have these visual cues to sort of switch between, one, almost like you're going between one stable state and another stable state. What's going on? There we go. Okay. So there's just sort of enough visual information to transition from one stable image, which is looking up, versus another stable image, which is looking down. Right? So to make a very sort of tentative connection to something a little bit more mathematical, this is almost like a bistable system. Right? So you have a potential, it seems like, that has two stable points. Let's call these stable points as, x hat and x check. So it doesn't matter which one is which. And, in the case of Escher's image, it's almost as if you're stuck looking at an image from below, but then there's some visual noise that sort of induces you to look at the image from above. So you're sort of moving between these two stable points. Now, of course, if I have a bistable system like this, and let's say that I have some dynamics that follow this equation, right, this ODE here. And let's say that my initial point is in one of these stable points, right? So I'm either in X hat or X check. Then I will never ever escape the stable point. This deterministic system just can't escape this attraction. You can't get out of it. On the other hand, the addition of even a tiny amount of noise. So for any positive epsilon, right? So if I introduce a quantity epsilon here, and I put some noise along with my ODE, then there is a positive probability of actually escaping these stable points for any epsilon positive, no matter how small it is. Okay, and this is sort of an interesting phenomena, particularly because you can sort of try to understand what happens if this escape probability is rare. If you're trying to model like the possibility of escaping as a very small probability event, right? And the real question is, how do you estimate or compute this rare event probability? Right? So this is a question that has received tons of interest in both the simulation, applied probability communities that I sort of broadly belong to, but also more generally in physics, computational physics. And there's a lot of ways of thinking about this problem. One really important theory in this setting is the so-called Friedland-Menzel theory. Okay, so I want to, in some sense, suggest a review of the Friedland-Menzel theory. So let's say that we start in X hat, right? So one of those stable points. And let's say A is a neighborhood of the other stable point, X check. Okay, so I want to ask myself, what is the probability that at the end of some time horizon, capital T, at some time capital T, this process X epsilon that we had previously will be in this state A. Okay, so I start in X hat, and I'm asking myself, what is the probability that after some finite amount of time, I will end up in set A? So some neighborhood of the other stable. And what Friedland-Menzel theory tells us is that you can establish what's called as a large deviations principle that says that this probability, oops, I don't know what happened here. There we go. Sorry. Okay, so what Friedland-Menzel theory says is that this probability is asymptotically something like e to the negative 1 over epsilon v star. So as epsilon goes down to 0, these probabilities are decaying away, and they're decaying away at an exponential rate, is what it's saying. And there's a specific exponential, rate function that I'm calling as v star here, and this v star is basically the value of a control problem. Okay, so L is just some Lagrangian. It's not so important right now what that is precisely, but it's just some Lagrangian, and it can be characterized completely. Okay, now modulos a lot of regularity assumptions, right? One can argue that this V star here is the solution of a specific Hamilton-Jacobi-Bellman equation. Okay, and there's a specific Hamiltonian associated with this. But the key point is the following: that if you optimize the Hamiltonian H, okay, then you can actually find out what is the optimal control to apply, so that you go from one stable state to another with high probability, right? So the computation of the optimal control immediately leads to an understanding of what is the most likely path that your process is going to take from the stable state X hat to a neighborhood of the stable state X check. Okay, and that most likely path will follow the solution of this SDE below. Okay, and notice that the control is sitting in here. Okay.
So the control is like a force you apply on the system
Exactly.
to change the Hamiltonian, the force will be from one.
Exactly. So the way to think about it is, in your original system, the probability of going from a stable state to a stable state is an extremely low probability, right? It's really tiny. So what do you want to do? You want to hopefully change the dynamics in some way that it makes it more likely for you to go from a stable state to a stable state, right? And the way you do that is by introducing this control. So you're changing the dynamics. In essence, you're changing the probability measure associated with this process, so that this rare probability is no longer rare under this new process. And this is like an optimal way of doing it. Okay.
Sorry, can I ask what is
Yeah.
the motivation for that?
For which?
Yeah, for intervening in the system and forcing it to change the dynamics.
Yeah, exactly.
So
So,
what is the application then?
so the application is, how do you estimate this probability, right? Like numerically. So you can actually now use this process to do importance sampling. Right. So it's essentially describing an importance sampling procedure.
It's like the buff sampling that works.
Exactly. Yeah. Yeah. So, you would use this if you had an understanding of this optimal control, then you can use it to do Monte Carlo sampling, right? So if you, if all that you had access to was a simulator, right? Then actually running that simulator and then directly estimating that probability up there is going to be really hard, right? Like if you did a Monte Carlo estimate of that probability, you would probably wait the life of the universe, right, to actually be able to estimate that.
And Peter asked what's the role of the time?
What's the role of time? So really the time is just saying that I will enter the set A at by some fixed time capital T. This is the time horizon of this problem. You could potentially, make this infinite if you wanted to. Right? Of course, that complicates the whole story with the Hamiltonian and so on, but it is possible to talk about infinite horizon. Hopefully I answered the question. But does that make sense?
I don't understand so well why you cannot estimate that directly, but.
So this thing?
Yes.
So you still have to solve the A shape here. So the way that you would use all of this is to find this sort of biasing, basically the biasing measure from this SDE, sample from this process, and then sort of take it back to your original process, and then estimate the original probability. So that's how you would use this whole theory in the importance sampling set. So it's essentially setting up an importance sampling. There's a question?
Yeah, I was just thinking in general, what kind of bound do you have on this phi? I mean, if this phi is orders of magnitude larger than this potential, then you can just completely let phi determine the whole solution. And so there must be some sort of very limited space that you're interested in that this phi can come from or not.
Well, phi, yeah, I didn't really specify it, but phi has to be in the class of absolutely continuous functions. So it's not some arbitrary function, right? And the absolute continuity over a finite time horizon is imposed on the kind of boundaries. So you're right. I'm sort of skipping a lot of the details.
Yeah.
Like if you look at the actual theory, all of these things come into play.
And what is adds to the actual theorem path sampling? What's the added value?
Sorry, what's the question?
Because you say this is equivalent to the path sampling, I think the field of path sampling. What's the difference and the added value for the path sampling?
So I think if you find this optimal control, the probability of encountering that event is higher under this optimally controlled process. So that's the value of this.
So
But when you're talking about optimizing the Hamiltonian, that depends on this X.
So this X here is a state, right? It's not a process.
No, I understand that, but in the bottom equation you have here, that's epsilon.
Yeah.
Okay. So can you still can you do this optimization separately from your X epsilon?
You can.
Okay.
You can, right? So, well, let me state that in a more specific way. So this Hamiltonian H here, it actually depends on this potential U.
Yeah.
And it'll depend on, well, epsilon won't be there. If you had like a diffusion coefficient here, that would be part of the Hamiltonian.
Yeah.
So, in that sense, yes, it depends on X, and you need to have some knowledge of the true process. Which actually brings me to my question, right? So how do you compute this V star and phi star if you didn't know, that underlying process? Right? What if you only had like sort of black box access to the system? So you go and you ask for a sample, right? It's like a simulator, it's like some complicated system. You have a simulator, you go and you ask for a sample path. In that case, how do you actually solve these types of problems? How do you compute V star and phi star, right? Here, this Hamiltonian depends on the potential and any diffusion coefficient that you might have. And what if you didn't know that, like explicitly? And what if it's not Brownian motion, but some other like fractional Brownian motion that's driving the system? So now all of a sudden, this is not a Markovian system, and this is it's a more complicated situation.
But you still know that there are two stable fixed points, or I mean, do you?
Yes, I mean, you would have to assume that there is some structure to your potential. Yeah. But this question is much more broader, right? In the sense that there are many problems in engineering and finance where I want to learn how to interact with the stochastic system, like without knowing precisely what the dynamics are. Sometimes some information, but in many cases you don't know anything. So for instance, in like high frequency trading, you might want to learn policies on how to execute buy and sell decisions in a market. And all you have is interactions with the market, right? So you make a decision, buy or sell, and what you receive is price information in return, right? And typically these price paths are not Brownian motion. They're much more rougher, and volatility we know is basically like fractional Brownian motion, right? So it's much more complicated. Similarly, in high-speed communication networks, particularly in like these switches. So here, this is an example of what's known as a crossbar switch. And I have a bunch of inputs. Okay, so think of this as traffic from, let's say, all the neighborhoods in Amsterdam, right? Internet traffic. And these have to be switched off into, pipes that go out to other parts of Europe, let's say, right? So, and you can't simultaneously switch all of these through, because there may be traffic on this input that wants to go to that output over there, and so on. Okay, so there is a constraint on how many simultaneous matchings that you can do, how many switches you can close simultaneously in this grid. But this problem becomes really complicated when these inputs are not sort of smooth processes. Okay, when the traffic coming in has like long range correlations, the computation of an optimal policy here becomes really complicated. So people try to use reinforcement learning to actually compute an optimal policy. But this is in a high-speed setting, you actually, in a high-speed setting, you actually want to do this almost in continuous time. And so, we're sort of running into this problem of how do we learn these types of policies when we know nothing about the underlying system, and we want to interact with the system and learn how to make good decisions. So that's sort of the broader picture. So, which brings me to this idea of reinforcement and a model of reinforcement. So in discrete time, it's very sort of natural to think about the reinforcement learning model in this sort of block diagram sense. So here you have an agent. Okay, so the agent takes actions, 80, at each time, and it interacts with the environment that is basically like a black box. Okay, so I don't know anything about what's happening inside of that environment, but I take actions, and in return, what I receive are 2 bits of information. One is the state of the environment. What happened to the state of the environment because I took an action in the next time step, and what kind of, there may be a reward associated with having taken a particular action, and this gets fed back to the agent, and the agent uses this information to decide on a future course of action, and so to repeat this over and over. Okay, so this is a very classic RL model. And the goal, broadly speaking, in reinforcement learning is to learn to take good or ideally optimal actions in an efficient way. Okay, so this efficiency is like, in some sense, crucial in reinforcement learning. Because, I mean, there's a sort of a donkey answer to all of these questions, right? I mean, what's the donkey answer to learn a good policy? Just interact with it as much as possible, right? And then you learn everything. But then that will take the age of the universe. It's not efficient, right? So you have to learn fast. So efficiency is important. But then, because you're sort of interacting with an environment, you're taking an action, influencing the state of the environment, and then receiving feedback from the environment, you sort of have an exploration-exploitation trade-off, right? And this is actually fundamental to reinforcement learning, and it's what distinguishes reinforcement learning from optimal control. Okay, in optimal control, where you know everything about the environment, there is no exploration-exploitation trade-off anymore. Okay, when you don't know anything about the environment, you might learn something, and you might decide, okay, I've learned enough, and I'll just exploit what I've learned. But then there may be better states, better actions that you can take that maximize your reward even more. Right, so there's this exploration aspect of this. So in some sense, what you want to do is you want to balance exploration with exploitation of whatever information you gain so far. Okay, and a natural question to ask here is, okay, what's a good strategy for exploring these spaces, like essentially the state action reward space? So these things are all tied together in some complicated way, and I have to explore the state action reward space. So what kind of a strategy should I follow? Right. So notice that any strategy that I follow has to both be a control action and something that helps me, sort of explore this environment. Right. It's not just about, gaining reward. I also want to find out what else I don't know about this environment. Okay, so one simple strategy that you can follow, and people have explored this to death in reinforcement learning, is the so-called Boltzmann or Gibbs or softmax control for exploration. Okay, this, in some sense, it's a very natural model to follow. So let's say that you're in a particular state S, and what this thing says is you randomize over the possible actions that you can take, A, by following a Gibbs distribution that depends on some kind of a value associated with being in state S and taking action A. And this is called as the state action value function or a Q function. Okay. And associated with this is like a temperature parameter. So if tau is positive, but if it's really small, right, if tau tends to 0, then you're sort of freezing this exploration. You're saying that this should become, sort of like a Dirac measure. On the other hand, if tau is large, then it's going to become more and more random. You're increasing entropy. So in a finite space, it's just going to be like a uniform distribution. Okay. So, you can see that this is, in some sense, a nice strategy to follow because A, it lets me take actions, but it's also sort of randomizing my actions so that I can also explore as I go along. But is this optimal in any sense? Right? I mean, it seems like a natural thing to do, but it's not clear that it's optimal in any sense. But it turns out that this policy, this Gibbs type strategy, is actually kind of optimal under what's called as maximum entropy reinforcement learning. Okay, so if you change a cost function, okay, and you sort of penalize any kind of degeneracy in your control policies, and I'll actually introduce this explicitly towards the end of the talk. When it turns out that Gibbs type controls are actually they're optimal in the sense that they will give you good exploitation, so you will get high reward, but you will also get good exploration. So you will try to find like a maximal amount of randomness with this type of policy, and you can actually compute one, for your problem explicitly.
Does this result assume that the system is Markovian, or that, given your state,
Yeah.
your action will always yield the same reward? Because it might be that, when you revisit the same state later time and it's not Markovian, you do the same action and you get a different result.
Yeah. So there is so a lot of the theorems that sort of establish this explicitly assume Markovianity of the underlying environment. And there is also an assumption of stationarity in a lot of this, right?
Right.
So what I show towards the end is that you can actually explicitly calculate a maximum entropy RL policy that's optimal, even when you have non-Markovian dynamics. So that it can be extended to that situation.
Sorry, can you sorry, it's the first time I hear this kind of stuff, so
Yeah.
asking basic questions, but what is that you're trying to maximize exactly, like?
So hold on to that.
Okay.
Because I'll show you an explicit function
Okay.
that, the type of thing that you would try to maximize. But typically what you would try to do is, you would want to look at like a cumulative reward, right? So this is supposed to be sigma. I can't write with this. So then you have RT, right? And this is in essence a function of, the state and the actions that you're taking, right? And you're trying to maximize this over different policies that you can follow. Okay. But I'll give you an explicit form for this.
So you're trying to maximize the reward, is this?
So you're trying to maximize the cumulative,
The key?
right? So you're trying to accumulate as much, reward as possible. So,
And how does that maximizes your exploration?
so if I have to explicitly penalize, not explode.
Okay.
So there is an additional component. So I'll introduce that.
Okay.
Okay.
And I'm sorry also about this question, but
No.
the word control,
Yeah.
bothers me because I don't exactly know all the contexts that it's used.
Okay.
What it exactly means, control? Is it a function like the one you showed before, control function?
Yes.
Okay.
Yes. So by a control, I mean, so that's a good question. So here I explicitly mean either like a randomizing control like this, where it's a probability distribution over the possible actions that I can take. Or it could just be like a degenerate function, right? So I'm in state S, and then just tell me, some C of C of X. So it could just be like a explicit, mapping from states to actions. And this distinction actually will be important. In fact, it's at the heart of this talk. Okay, so what we want to understand, in essence, in this paper is how do you do exploration in high frequency or continuous time settings, really continuous time, and with non-Markovian dynamics. Okay, and ultimately, can we show under some conditions is this Gibbs type distribution still optimal in these types of settings? Okay, so before we get to that, right? And let me talk about classical optimal control, introduce a lot of these concepts and functions that we want to optimize, and then also classical stochastic optimal control and how it builds on top. So in control, the way that one sets up a control problem is you start with an explicit state model, and that state model is typically an ordinary differential equation that's controlled. Okay. And the control, if you notice here, is sitting inside of this function B, this vector field. you should think of ut as a function of time. So, or rather u. So u is going to be a function from 0, let's say capital T, to u. And this u is typically a subset of RT. It's supposed to be RT. And our objective is to maximize over all such possible control functions this cost objective. Okay, so this cost objective has two parts. The first part is sort of a terminal cost. Okay, so the cost of, for instance, in the case of the where I started this whole talk with rare event estimation, you could ask yourself, this could be the probability of not hitting a particular state, or the probability of actually entering a particular set, for instance, okay, at the end of some time. But you could also have like a sort of running cost. So this is like you're accumulating a reward or cost over time. So going forward, I will use the terminology reward, just because in reinforcement learning, one tends to maximize over these functionals, okay? Whereas in control, one tends to minimize over these functions, but mathematically, they're all equal. So this is the type of objective that one tries to maximize. Okay.
When you talk about penalizing, not exploring, what is the term here?
That's not here yet.
Ah.
It's not there yet. Yeah. In fact, that will not come back till the end of the talk, right? But then it will become clear. Okay, so what we're interested in is the optimal value. Okay, so V star. And this V star is basically, I probably should have written it, but so V star is essentially soup over U. The soup over U and J of U. Okay, so what we want to do is compute this optimal value. And this optimal value has to be computed at all possible initial states x0. Okay. And we also actually want to compute it at any point in time. So we can sort of write down a value function of starting at any point in time, at any possible state, and then what is the value of taking optimal actions from that point onwards. And this can be explicitly characterized as the unique solution of a Hamilton-Jacobi-Bellman equation by using the dynamic programming principle. And the HJB, if you notice, has an explicit form here for the Hamiltonian. So this is exactly what I'd written earlier, but more explicit. So B is our vector field here. R is our running cost. And this gradient of V is basically the gradient of the value function. And this is exactly similar to the HJB that I showed earlier. There is a terminal condition, of course, on this that depends on the terminal cost of our control objective. Okay, so this is in the case of deterministic systems. Given these equations, you might ask yourself, okay, how do I do reinforcement learning in this setting? Suppose that I didn't know anything about the system dynamics. In other words, maybe I know nothing about B, and maybe I don't even know R. And I want to estimate the optimal value function and the optimal control in this setting. And then what you would try to use is just these paths. You view this system as a black box, so I can ask for paths of this environment by taking actions. And you can, and there's been a tremendous amount of work around using reinforcement learning for this setting. In fact, there are two broad categories of reinforcement learning methodology. One is what's known as model-based reinforcement learning, Okay, so in model-based reinforcement learning, you will first estimate the system model. In other words, you try to estimate this B in this case. And then you try to compute an optimal value function, and you start using standard control methods. Okay. Alternatively, you can also do something called as model-free reinforcement learning, where you don't try to learn the underlying dynamics, but you directly try to estimate the optimal value function in the control. Okay. Now you can, why should you use one versus the other? Yeah, go ahead.
In this model-based reinforcement learning, you want to estimate B, but B depends on you.
That's the complication.
So that's a kind of chicken and egg problem, I would say.
Precisely. Yeah. Yeah. So it's
Is it then an iterative process that you're doing? Okay.
Yeah. So you would typically these methods. So there's there's a whole zoo of possibilities. One possible method here is something called as an actor method. Okay. So basically you parameterize these control functions using some function approximators. So and then you try to estimate these parameters by doing stochastic approximation, for instance, gradient descent. And you try different actions as you go along, and then hopefully your estimate of this system dynamic will converge to the truth. So it's a folk theorem, I would argue, that people believe that model-based reinforcement learning is somehow more sample efficient. Like you need fewer interactions with the environment to learn relative to model-free reinforcement learning. I mean, in some sense, model-free reinforcement learning, seems like it should be, worse from a sample efficiency perspective than model-based reinforcement learning, because you could have learned, this value function. Your estimates can be very, very noisy and heavily dependent on the actions that you're taking and the policies that you're following. And, but there's no theorem as such that shows explicitly that one is better than the other. Okay. This one side. So in this talk, really what we are focusing on at some level is on this model-based reinforcement learning set. Okay. So we want to know how to explore the environment, the stochastic environment, to in essence learn that system dynamic. There's a question.
Yes, I was wondering. So you said what iterations for this, I guess, for this approach to converge to some reasonable value for P star and U star.
Yeah.
But this means that your capital T has to be short, or.
So, good question. So typically, reinforcement learning algorithms are run in an episodic fashion. Okay. So you have a finite horizon, but then you have many, many finite horizons. Right. So you're learning over a finite horizon, but then you're repeating that finite horizon many, many times. So it's in essence, you could maybe think of it as an infinite horizon problem.
The last time I saw these kind of problems was laughing, and they were still doing, things like greenhouses. You need to optimize your heating for your greenhouse in order to produce maximum amount of crop in your greenhouse. So then you're talking about, let's say, a period of 2 months. But if you're talking about a period of 2 months, you can't just endlessly repeat that.
Well, in simulation, of course, you can.
Yeah.
Right? And a lot of these things are simulation methods.
Yeah.
In practice, if you, that's where the whole efficiency part comes in. So if you were to run these algorithms in the field, let's say, like in this example that you had, then you need to hope that your learning method is fast enough that it will learn within a few days, right, in this setting. So there are no guarantees on that, right? Like one has to look at the time scales involved and decide whether it will run fast enough. It's a good question. Yeah. Okay. All right. So how do we extend this, this framework from deterministic dynamics, right? So here we're still talking about deterministic dynamics to systems that have stochastic dynamics. And a very natural way to do that would be to just introduce Brownian motion. So add like a Brownian component to our controlled ODE. And now instead of maximizing this cost function on the inside, you put an expectation on this cost function, right? So this takes us into the realm of stochastic optimal control. And in the case of stochastic optimal, the stochastic dynamical systems, learning the dynamics now is much, much more complicated. So when you don't know the underlying model, you have to somehow learn these SDEs, okay, these stochastic dynamics. And as I noted before, the RL strategy to learn these dynamics would be to use a policy to both explore and exploit. And there is a problem though, when it comes to these stochastic dynamical systems. The control U, we're still computing a control function. Okay, it's a function of time. And in essence, it is, as I pointed out earlier, this control U is going to be something like, oops. So at each point in time, if I'm in a particular state S, this control U at time t is basically going to be some function of S. Okay, so it's a deterministic mapping from the states of the environment to the actions that you can take. But a function like this will not facilitate any kind of exploration, because every time I encounter the state S, I'm taking the same action. Right? So I don't explore. What I want to do is, if I encounter a particular state, I don't always want to take the same action. Sometimes I just want to randomize. Right? I want to take a random action, something that will help me gain some information about the underlying stochastic environment. But a policy or a control function like this will not allow us to. But it's not clear how you can get a randomized, controls into this framework going. And that's sort of the crux of our problem. Like, how do you introduce like a randomized control into these types of dynamics? And in fact, the notion of control itself changed, because when you do stochastic optimal control, what you gain are these types of control functions as your solutions. And that's just the definition of stochastic optimal control. So one has to go beyond stochastic optimal control to some notion of, computing like randomizing control. Yeah.
This does depend on the fact that you assume that the noise is not dependent on the action.
Yeah, that's very perceptive. So yes and no. From a theoretical perspective, if you want to guarantee the existence of controls in these types of systems, it is better or easier, let's say mathematically, to not have controls in that, let's call it the diffusion coefficient. Yeah. Because if I put a control there, then in theory, I can push this system to any possible, outcome. Like I can maximize reward as much as I want, which is a bit crazy, right? You shouldn't be able to like instantaneously go to like an infinite reward situation. So it makes it harder mathematically. So
on the other hand, you gain exploration.
But you've already maximized reward, right? So but you haven't learned anything about your underlying system in some sense. Yeah. So it's so this is one of the reason I didn't put it there. I mean, in theory, you could have the control in this part, and people have studied it. But then you have to somehow relax the notion of the control, the control space. Okay. And in our theoretical development, we don't do that. But I point out at least one paper that sort of deals with this situation as we go along. And one final change in the model is we want to move away from Brownian motion, right? The moment you introduce Brownian motion and you have these types of dynamics, right? So this process XTU, right? The solution of this STE is necessarily a diffusion, ergo a Markov process. Okay, so it has Markov dynamics. And not all stochastic environments, as I hopefully convinced you, are Markov in nature. So we want to look at systems that are not necessarily driven by Brownian motion either. Okay. Okay, so the generalization that I want to introduce to so that we can have exploring controls, not just these sort of standard stochastic optimal control functions, is through this notion of what's known as relaxed controls. So relaxed controls were introduced in optimal control theory in order to argue for the existence of optimal control. Okay, they were not intended to be used for exploration necessarily, but they turn out to be sort of the appropriate framework here. So in an exploratory system state dynamic, what I will do is I will replace this control function u here, okay, by a control function that is, a probability measure value. Okay, so a very obvious thing to do. But then, how do you incorporate that into the system dynamic? That's really the question. And it turns out, a very natural way to do this, I would argue, is to say that this vector field here is in some sense averaged over by the randomizing control that I'm going to use. Okay, so that's why I'm going to introduce the optimal, sorry, not the optimal control, but this relaxed control into this system dynamic. Okay. And I'm still going to let it be driven by Brownian motion for the moment. And the cost function now slightly changes. Instead of optimizing over control functions, I'm going to optimize over measure valued controls.
Sorry for what do you mean with this mathematical P that you said gamma should be an elemental?
Yeah.
What set is this?
Yeah, okay. So this is the probability measures. So probability measures on U. So gamma is going to be a map from 0, let's say T, to the space P of U. Okay, so it's all possible probability measures on the space. Okay. And then the second generalization is, okay, how do we get rid of Brownian motion in this setting? So, what we observed in practice is that the observations of systems like, in that high-speed network or in finance, these price paths don't look like Brownian motion, right? So they look a lot more volatile. They look worse, quote unquote, than Brownian motion. So one way to think about that is that they have some kind of Holder regularity that is different from Brownian motion. Okay, so if I look at the Holder continuity of the sample paths of these processes, that Holder continuity is different. And one sort of natural generalization perhaps would be like fractional Brownian motion. And so fractional Brownian motion, if I look at a scalar fractional Brownian motion, its correlation function roughly sort of looks like this. So look at the time increment, t minus s, and then you raise that to the power h, where h is between 0 and 1. But I think better to look at some images. So when h equals 0.5, right, so the middle figure here, this thing is Brownian motion. That's a sample path of Brownian motion. If h is closer to 1, okay, this sample path, in this case, h equal to 0.7, you can see that the sample paths are somehow smoother than Brownian motion. And so what does that mean? It means that there is stronger correlation over time intervals, okay, non-overlapping time intervals. One of the definitional properties of Brownian motion is non-overlapping intervals have no correlation, i.e. independence, because it's a Cauchy distance, right? On the other hand, if h is less than a half, over here. Oops. So let's say h equal to 0.3. Well, this path looks, quite jumpy relative to Brownian motion, right? And so it's sort of, in some sense, less correlated. Is it? From if you look at non-overlapping intervals of time, the sample paths of this process are somehow less correlated compared to Brownian.
Are the sample paths still continuous in this case?
Yes, they are. Of course, continuous with respect to which topology is the question, right? So it's continuous. So if you look at Brownian motion, for instance, it's continuous with respect to the Holder topology for any Holder coefficient larger than at least one. Okay. Okay, so all we have to do now, replace Brownian motion by fractional Brownian motion, right? No, very simple, but unfortunately, no. So what do we need, right? So if we have an equation like this, we need to be able to talk about it. If we try to solve this equation, we need to integrate this. So we need to be able to integrate this guy. This sigma of t xt dbt. So we need to have some notion of integrals of this form. Well, here's some basic facts about fractional Brownian motion. This is true for any h not equal to a half. Right? If you're Brownian motion, then you're definitely Markov and you're definitely martingale, not finite variation. But Markov and martingale properties turn out to be crucial in order to talk about the stochastic integral that we're trying to define. Okay, so if h is not equal to a half, then you're not Markov and you're not a martingale. So the immediate consequence of this is that you cannot use Ito's theory. Okay, so Ito calculus is not available. Right? So this is how you would try to solve these STEs using Ito calculus. And instead you need some other, notion of integration. You need some other integration theory. And what we will use in this paper and in this talk is the so-called rough path theory. Okay. So now I don't want to get too much into the details about rough paths. I'll come back to it, right? And give you a very sort of high level, hopefully understanding of what rough paths is. But the 100,000 foot, notion of rough paths is, think of it as a way of defining integrals of this form. And it lets you define integrals of this form and solutions of differential equations, as we saw before, regardless of what these processes are. Okay, and it is incredibly versatile, and it's in fact just the right way to think about this problem, as we'll see. Okay, so in some sense, rough path theory subsumes Ito's theory as well. Okay, in order to define these integrals using rough path theory for fractional Brownian motion, for instance, then you will have to use the regularity of the fractional Brownian motion path. Okay, the sample path regularity. And it'll also crucially, in some sense, depend on the Gaussianity of the fractional Brownian motion, but rough path theory is much, much more general. In fact, we don't work necessarily only with fractional Brownian motion. Our theory works more generally. Okay, so here's our setting. So we have a relaxed control viewpoint. So we want to do exploration. We're going to introduce relaxed controls. We have a rough environment. It could potentially be a fractional Brownian motion. It's more likely something else. And that's also included in this. And I'm only going to do what's known as pathwise optimization. Okay, no expectation in the cost function. And towards the end, hopefully we get there. I'll point out why this is a hard thing to do. Why solving expectation cross-functional is hard in this setting. Okay, so here's some prior work in sort of similar questions in the control setting. None of this deals with relaxed controls. All of these are like classical controls. In the case where you have really nice driving signals that are, like fractional Brownian motion with alpha or the Holder coefficient larger than a half. There's a paper by Masliak and Mizar that does not include Brownian motion, for instance. where they actually characterize optimal controls in this setting. There was a follow-on paper by Lee et al. In 2017, where they actually looked at the case with Brownian motion, but they had no control in the diffusion coefficient. Okay? And explicitly for the reason that I pointed, it becomes really hard to talk about these controls. Allen and Cohen, on the other hand, introduced the control into the diffusion coefficient, but they had to restrict the class of controls that they produced. But they were also looking at alpha greater than a third setting. And in the case of pathwise optimization, there is a classic paper by Lyons and Tsouganides, where these ideas of pathwise control was actually first introduced. And in the case of fractional Brownian motion, Bhakta and Ma from 2007 really characterized optimal controls, well, classical optimal controls for fractional Brownian motion in this pathwise optimization setting. So our work sort of builds on top of some of these things, but we also have some new results as well. So finally, our framework is the following. So we have a state process that follows these types of dynamics. The control, the relaxed control is in the drift part of this equation. No control in the, let's call it the diffusion part or the stochastic part. It could be driven by any kind of a rough signal. Doesn't have to be fractional Brownian motion necessarily or Brownian motion necessarily, but we do want the Holder regularity to be at least 1/3, right? So the roughness is in some sense restricted. And this is really for convenience, mathematical convenience, I would argue, not necessarily a technical restriction. But if you put a bit of effort, you could extend everything that we've done to more general settings. The control space consists of these probability measure valued functions. Oops. Can't write it for some reason. So P2 is a subset of the earlier P that I showed you. Essentially, it consists of probability measures that have at least 2 moments. And we need that so that we can talk about the Lipschitz or the Holder continuity rather of these functions. So we're assuming that these functions gamma are Holder continuous in the Wasserstein 2 distance for any epsilon, for some epsilon positive. And then our cost functional looks something like this, right? So F is some general functional that includes everything that I talked about before, but also other things, as I'll point out in a few slides. And what we're interested in is this optimal value, right? So we want to know what is the maximum value that I can obtain by following an optimal policy, okay, for this type of system. Yeah.
Why do you now integrate from S?
So it's a slightly more general problem. You could fix it to 0 to t, but this is for every s between 0.
But S is a time here or is it state?
S is time. Yeah. Okay. How much time do I have? Am I on?
We are now sort of over the hours, so
Okay.
we're running in extra time.
Okay. I'm sort of towards the close to the end, but let's see. So the first result that we have is that an optimal relaxed control actually exists. I mean, natural standard result to ask. And the story of this result is you assume enough, and of course, it's always true. Right? So, so if we assume that
Assume that it exists, so
yeah, exactly. Not that egregious. So if we assume that these control functions take values in a subset, a compact subset of the overall space of probability measures, then our space nu epsilon, so remember nu epsilon is this control space here. It consists of these functions that are sort of Holder continuous in Wasserstein space. These things are also compact. And if we place some restrictions on the cost functional and the terminal cost, then what we find is that the supremum is achievable by some optimal gamma star in our class of potential control functions. Sort of unsurprising. I think the more interesting problem is how do you characterize this value function, the optimal value function? And this is where, we want to say that it is the solution of some kind of an equation. Right? That's the natural characterization of this. And that comes through what's known as the dynamic programming principle. Okay, so what the dynamic programming principle essentially says is, let's say that I'm following an optimal policy, and I implement this optimal policy at this time instant. Then if I encounter these states at some point in time in the future, the same state, then I should apply the same policy, right? So that policy should remain optimal at all points in time going forward. So that principle lets us break down this value function as the cost over some small time horizon plus the value function going from that point on. Okay, so the cost to go from that point on. So this is this equation here. So notice that it's an equation, right? So to know what the value function is, you need to solve this equation. But this can be written down in terms of a differential equation. So there's a differential form for what is written above, and that differential form is a partial differential equation. It's a nonlinear partial differential equation. And we've already encountered it. It's the Hamilton-Jacobi-Bellman equation, the HJB equation. And the HJB equation here has almost the same form that we saw earlier in the case of the deterministic optimal control. Right, so the same sort of similar Hamiltonian here, if you notice this. What's different is, of course, we have like an integration over the drift function. But also, there is this extra term. Okay, so this extra term involves the driving rough path. Okay, so that's what turns this Hamilton-Jacobi-Bellman equation into what's called as a pathwise HJB. Okay, it's different from what we saw earlier. It's not same as the HJB that you get in stochastic optimal control. It's not the same as what you get in deterministic optimal control. And you have this extra term that depends on the underlying rough path.
Sorry, I missed on. You assume the dynamic programming principle, right? Or
yes. So you assume that
you assume that this holds. Okay.
Yes. Yeah.
And then you get this.
Exactly. Yeah. But also there's one more assumption. Right? This value function that's coming from the dynamic programming principle is the solution of this HJB if you assume that it's an element of C1. In other words, the value function has to be differentiable with respect to the state because you need the gradient here, right? But that's actually never true. Like the value function that comes from the dynamic programming principle is actually not C1 in most cases. This is a well-established fact. So it cannot be an element of C1. But we know that HJBs exist, right? You can always write down the HJB without actually talking about DP at all. So seemingly there's a disconnect. In fact, this was a major problem in control for a while, until an appropriate notion of a solution was discovered. And I'll talk about that in a moment. Okay, so we need a detour at this point, and this is where I'll actually, hopefully, not confuse you about that theory. Notice that if we go back for a second here, so in order to talk about, ignoring the fact that we, maybe not an element of C1, but suppose that you write down this HJB, to solve this type of equation, you need to know how to integrate, these types of objects, right? So in other words, we need to give meaning to these types of integrals. So this is like a slightly more generalized form of what I had in the previous slide. So how do we talk about these types of integrals where we're integrating against a rough path? Okay. So for instance, X could be fractional Brownian motion, or it could be some other alpha order path. So in order to talk about that, I think it's useful to sort of step back and look at a toy model. Okay, so a toy model where we have an integral that looks something like this. Everything is scalar. X is a scalar path. And I want to define, this integral somehow. And for now, our assumption is that X is in is Holder continuous with alpha greater than a third. Now, if I take this integral, and I just take this vector field V, assume that it's nice enough that all its derivatives exist. Okay, and I do a Taylor expansion on this V over here. Okay, simple Taylor expansion. Let's look at the first two terms in the expansion. It'll look something like this, right? So you will have V of XS. You'll have this guy into the increment of the process. Right? The increment of the process is well defined. Then you have the first derivative of the vector field. And then you have this x2. So x2 is this iterated integral. You need this x2 to be well defined. So this is one of the main assumptions in rough paths, that you can actually define this appropriately in some sense. Now, if, and of course, this comes up again in this final term over here. And you can define this iterated integral using like classic methods if x is sort of nice and smooth, in the sense that it is not smooth, but it is less rough than Brownian motion. So if x is like has a a Honnappa coefficient larger than a half, then there's something called as a Young integral. This is like a classic result from, I think, the 1910s, maybe 1920s, that sort of and Young defined these types of integrals explicitly. So it looks sort of like a Riemann-Stieltjes. Okay. So this notion of integration makes sense. The question is, how do you extend it from alpha greater than a half to alpha between a third and a half? Right? I mean, how do we do that? So one way to do this is to take your path and sort of do a piecewise linear interpolation over a mesh. So you sort of have like a continuous path. And then you can set up these integrals. These integrals are now well defined on this piecewise linear path. And the first assumption in rough paths is that these piecewise linear interpolated paths that are obtained from any rough path that is C alpha continuous, in other words, alpha greater than 1/3, that these x2n's, these iterated integrals, converge to some x2 in an appropriate topology, okay, in an appropriate topological space. So this is an assumption. And in the case of where x is Brownian motion, right? So alpha is 1/2 in that case. Then x2 will turn out to be what's known as the Stratonovich integral. So there's like an explicit characterization of these double integrals in that case. Rough path theory lets you go beyond this, and you can talk about these. It gives you a way of defining these iterated integrals in a much more general way. A second assumption that can be relaxed, but we'll go along with it for now, is that these vector fields are all smooth. Okay. So to summarize, what rough path theory lets you do is you can define these integrals as well as solutions of differential equations, and through these sort of linearly interpolated paths, so these y and t's, they will converge to some objects y. And in essence, rough path theory lets you take these well-defined iterated integrals along with smooth vector fields to define integrals and solutions of differential equations as necessary. So this is sort of the high-level million-foot, view into rough path theory. It's obviously a lot deeper than this, but it's enough for us to understand that we can, assuming that all of that holds, we have a notion of a solution. We can integrate equations of this form. But the question is, what kind of solution can we obtain if we were to integrate? Because we know that the value function in general is not C1. Right? It can have kinks in it, right? So the value function could have points at which it is locally non-differential. So the solution notion that you want to use is what's known as a viscosity solution. Okay, and the idea of viscosity solutions at a high level is, how do you transfer derivatives that you don't have, onto test functions? Okay, and in fact, it turns out that it's been shown that in the case of value functions that come from dynamic programming itself, they are necessarily viscosity solutions. Okay, so it is actually the right way to think about value functions coming from dynamic programming. Okay, so the way to think about viscosity solutions is, let's say that this sort of piecewise linear function here is our actual value function. So I have these points where I'm not differentiable, and I'm going to introduce derivatives that, test functions that have derivatives precisely at the points where my value function has no derivative. So locally, I'm going to sort of approximate the behavior of the value function by these smooth C1 functions. And let me skip over this intuition, the last bit. There is a problem still, which is, in our case, these value functions can't just be C1 functions. They also have to somehow have the regularity of our driving rough path, right? Because if you go back and look at the PDE, we also have this term. So somehow our test functions must have just the right amount of differentiability as well as the roughness of our driving signal in order to define an appropriate notion of a solution. And so that's precisely what we do in the paper. So we carefully define a class of test functions. So if you had no rough path, then you wouldn't have this term, right? And this is the classical notion of a viscosity solution. That's used extensively to solve these types of nonlinear PDEs. But with the rough path in this pathwise optimization, we will define our test functions to include this term. And now using this, we have a notion of our viscosity solution. Essentially, what it says is if I look at the so I think the way that I would want to write this, maybe I shouldn't have skipped what I skipped over there. So anyway, so if I look at this this equation, this inequality here. Consider this. You can write this thing down as psi plus soup over h is less than or equal to 0. Okay. And this is exactly what you get with the true value function. So with the true value function, I would have dou t b plus soup over h plus this last term. Okay. So in essence, what the viscosity, a solution to the actual HJB up here will be a viscosity solution if it both upper bounds and lower bounds the test functions in this sense. Okay. And this is in some sense, it's sort of using the notion of monotonicity of the dynamic programming operator. Okay. And that's how one would intuitively think about these viscosity solutions. But in any case, I mean, the solution to the HJB is the viscosity solution, and it satisfies this. And the main theorem in the paper is the following. So the value function that came from dynamic programming is in fact a unique rough viscosity solution, as we've defined, of this HJB equation. The proof is non-trivial. I really won't get into it. But it uses some ideas from flows and and let me skip over that. It's just a little beyond what we need here. But I want to tie this back to reinforcement learning. Nothing that I talked about so far really has any connection to reinforcement learning. The connection is through exploration, right? So if we go back to the so I mentioned maximum entropy reinforcement learning. So here's the objective, this capital F here, that incorporates a penalization of not exploring, right? So I have a term. So this is sort of penalizing entropy. Right, so gamma t is my probability measure. Gamma t dot is the density function associated with the probability measure. And I'm going to penalize any kind of degeneracy, right? So I want this entropy to be larger than zero. And of course, it's differential entropy, so I guess it should be negative infinity. But anyway, so if I use a cost functional like this, right, and everything that we've done so far sort of encompasses the setting, then if I use this entropy regularized objective and I optimize the Hamiltonian in the HJB. So in the place of F here, I introduce this entropy regularized objective. Then a little bit of calculation immediately tells us that the optimal policy in this case has this sort of Gibbs distribution form, just as what's been observed in discrete time settings with Markovian dynamics. The difference here is, of course, the lambda here, the temperature is basically this Lagrange multiplier there, and the control, right, this policy actually depends on the underlying rough path implicitly through this gradient of the value function. So there is sort of a pathwise dependence in this particular form. Now, there is a problem, of course, which is this V is not smooth as we talked about. Right? You have to use the notion of the viscosity solution to actually define the gradient. So you have to use some kind of a generalized gradient in order to make this Gibbs exploration strategy make sense. But this result, it sort of fully generalizes this result from Kim and Yang in the ODE setting. So they find a solution that looks rather similar, but it doesn't depend on the underlying driving rough path. The nice thing is, you can see that if I penalize degeneracy of these exploration strategies by using entropy, then the optimal policy to follow is necessarily a Gibbs type strategy, okay, even in the non-Markovian setting. Okay, so one last thing. So what we didn't do in this work is try to optimize expected costs, right? And now this is important because if I have stochastic dynamics, in essence, why am I using stochastic models? I'm using a stochastic model because I have uncertainty about the future, right? I'm modeling that uncertainty. And when I have uncertainty, I really want to resolve that uncertainty by using some kind of a function, like a risk function. And a natural way to resolve that uncertainty through a risk functional is to take an expectation of my cost objective, okay? And this expectation here is with respect to some path measure on the underlying rough path. But it turns out to be very, very hard to actually talk about the value function of these types of expected costs when the driving signal is not Brownian motion and you don't have veto calculus. And one idea is in this paper by Deal that I pointed out earlier, where they use what's called as a pure dual form by essentially looking at the pathwise control problem. So the pathwise control problem is essentially saying that, well, I know precisely which path of the future is going to appear, right? Because I know what the rough path is that's driving the system. So there's no uncertainty about the future in that sense. And I'm computing a control policy or a strategy that is in some sense dependent on that particular path. And so in control theory, that's actually called as anticipative. I'm anticipating what's going to happen in the future. What you want to do when you're trying to resolve uncertainty with a risk functional is you want to compute what are known as non-anticipating. You don't have information about the future. There's no prevision into what's going to happen. So in that case, what these guys do is that they introduce a penalization or a penalty for knowing the future. Okay, and so that's in the form of some kind of a martingale. And then they formulate like a max-min type problem like this. And this value function here turns out to be precisely, I didn't mean to do that.
You can press it again.
This double,
Double tick again.
yeah. Okay. So this value function here turns out to be precisely the optimal value function corresponding to this problem. Okay. Anyway, so this was done in the case where the underlying driving rough path is basically Brownian motion plus those iterated integrals that the Stratonovich rough path. How do you extend this from Brownian motion to even fractional Brownian motion is unknown, right? And really hard. It's something that we're working on right now. But this is an open problem. Like, how do we go from this pathwise control to like expected controls? And more generally, what if I'm resolving this uncertainty not through expectation, but through like some risk functional? Does the dynamic programming principle even hold? Is it time consistent? And therefore, is there an HJB? All of these questions are open. So these things are. Okay, so that's the end of my talk. Thank you for your patience. And
yeah, thanks for the talk.
thanks.
Yeah, can I ask a question?
Yeah, of course.
So I was just wondering, did you apply this to anything?
Uh-huh.
Like did you use some,
No.
some data? Did you...
I'm hoping that people here will apply it. Yeah, no, this is purely theoretical at this point. Yeah.
So you didn't do any simulation for anything? You didn't, no, just theory?
No, this is purely theory, this paper. Yeah, but so I have a student working on some questions around optimal transport, where we're hoping to use this framework. But I think we are not at the point where we can actually use it in simulation yet, because there's no method yet. Right? So what I presented so far is like a framework. So the question is, okay, how do I explore? Like, what is the right model to use to explore in continuous time non-Markovian settings? And this is one, I would say, appropriate model. It's not the only model, right? Like, you could sort of think about, really the question is, if we go all the way back to this equation here, and you look at this, this guy. Now, I introduced the exploration policy by averaging over the vector field. But is that the only way to introduce the exploration policy, right? Maybe the vector field itself depends on the probability measure, not through some integration, but through some other function. So it's not, I'm not saying that this is the only way, but this is a very natural way. So it's one framework, there could be more. So, yeah.
In the beginning, you said that stationarity was also an assumption to apply optimization.
Not in this setting.
Not in this setting.
Yeah.
This setting actually can have non-stationary.
Yeah, because if you notice, so B can depend on T, right? And also, so you need stationarity when you have an infinite horizon. Then if you're learning, I mean, hopefully you're converging to something in the infinite horizon, right? So typically people look at discounted cost, discounted expected costs, or long-term average ergodic costs. So then there's some kind of a stable, like stationary state that you're converging to, and sort of learning that. Yeah, so here we're looking at finite horizon control, and yeah, in that case you can allow for these types of non-stationarity. But I was going to say, like, there's no methodology. So how do you actually do reinforcement learning with this framework? So now we need to think of algorithms for actually doing this. And so that's part of our ongoing agenda. But if anybody's interested in working on this together, you're welcome to join. I think this is like a proper frontier in this area.
But another question I had about, like, so in your reinforcement learning, you basically said, okay, you have this environment, you have the actor, you have the state, and but if the environment is a complex system,
yeah,
it might actually, the system itself might change in dimension. Have, it's what's going on in society all the time, right? We invent something, and then suddenly a system has a completely different, lives in a completely different state space than originally.
Yeah.
Do your methods still apply then, or is it still, or is that really a complication?
So, the methods. So I think all the guarantees go out of the way.
Yeah.
I mean, because they explicitly assume that the dimensionality of your problem is known. It's not changing over time. Things are reasonably stable.
Yeah.
But if you have a system where the dimension of the environment is changing, I guess you could apply the method. But I suspect it will not work. Yeah. So are those the types of systems that you would think of applying this to?
No, I wasn't thinking of applying it at all, but. Sorry, I was just more, I just wanted to understand the limits of.
Got it.
Because I think that very many real world problems right now.
Yeah.
Actually have to do with the system itself changing.
Right.
In complexity.
Yeah. Okay.
And we want to have, of course, you want to have methods to somehow find an optimal way to deal with it.
So I think there is one way to, now that I'm hearing what you're saying and thinking about it a little bit more, there is another notion of what's known as a partially observable MDP.
Okay.
Right. So there you don't actually observe your actual, system, but you observe like a kind of a noise version. So it's possible that if you have like a rich enough description of your system, that maybe that's evolving in a much higher dimension, and then what you're observing is like a projection of that onto lower dimensions. Then I think you could use form DPs in this. So none of what I talked about today is actually dealing with partially observable entities. That's a significantly harder problem. But that might be a way to think.
You mentioned the possibility of application in finance. Do you see any more specific target for this control, like interventions or this kind of things?
In what?
In finance?
In finance? Yeah, people use reinforcement learning extensively, and in fact, even rough patterns in finance. And off the top of my head, I'm trying to remember, I think there's some folks in France, I think, who've developed some algorithms for systems driven by Brownian motion and using reinforcement learning to learn trading strategies. So this as well. This could potentially be used. I mean, if we come up with a methodology, right now we only have this framework. We don't really have any algorithms yet.
I have a question online, if I may. I hope you can hear me.
Yeah, we can hear you.
Yeah. Okay, great. Thanks, Harsha, for a very, very nice talk. Unfortunately, I couldn't be at EOS today. So I have a question about this. Also shown on this slide, the expected cost that you want to optimize here. I was curious whether it's also possible to somehow extend that or incorporate information on the variance. I mean, suppose you want to optimize the cost while also minimizing the variance, or I don't know, maybe have some information on that. But in particular, if you want to minimize that, right? Because it's nice if the expectation of the cost is optimal, but the variance can be huge. So that can still be a bad policy to take then.
Yeah, no, that's a really good question. The problem with the variance is, I think the dynamic programming principle may not hold anymore. Right, so you need, in order to use the HAV equation, if you go all the way back, let's see. Oh, there we go. So the DP principle tells us that something like this should hold, right? So the value at the current time, S1, should be, the maximization of the instantaneous, reward, let's say, plus the value from the time S2 onwards. Right? And if you use the reason why this works is because we're using expectation as our risk functional, if you like. And if we use variance, then all of a sudden you have this quadratic function sitting there. And I think this equality may not hold in that case. So in general, with these types of risk measures, you have to worry about whether the dynamic programming principle itself holds. And I think that could be a restriction on being able to use standard RL methods. People have looked at, what are known as convex and coherent risk functions, where the dynamic programming principle has been shown to hold. But I think that is not the case for variance. I can check that and get back to you. I just want to hedge it. But I think it doesn't hold for variance. Does that make sense?
Okay, yeah. Yeah, so, okay, I understand. So this principle will be violated then.
Exactly, yeah. And this principle is crucial because it's, it's what leads to the HJV equation. Of course, the HJV probably exists as an object by itself, but there's this connection to the DP principle.
Yeah, okay, clear. Thanks.
Yeah.
I think it's a nice time to thank the speaker again, and then we go for lunch.